So, we now will start talking for few next lectures on the science based foundation of steel making, because steel making involves a lot of fundamentals, and no course in steel making I think can be appreciated unless the fundamentals are known. Of course, I am not going to give you a complete coverage of the topics, but it is important for us to revise a few key concepts and show you that what are the fundamental components or the science based foundation of steel making, which we need to remember all the time as we go and address steel making problems, be it process analysis, process design, optimization, and so on. Now, steel making is more than 150 years old. When Sir Henry Bessemer first made steel by blowing air into a clay crucible containing molten pig iron, and since the days of Sir Henry Bessemer, this making and treating and shaping of steel has undergone remarkable improvements. Today, if you go to the BOF shop, for example, you are talking about 92 to 94% of yield in BOF. So, that means if you charge 100 kg of iron into pig iron into BOF, you are going to get something like 92 to 94 kg. So, it is extremely efficient process. In the BOF, the refining in the ALD converter and combination blown reactors, the refining is so fast, so rapid that you can get something like 2 to 3 kg of carbon per second. That is the rate of carbon removal we are talking about. If you go and visit the casting bay, for example, in a thin slab casting shop today, you will find that you are talking about 6.5 to about 7 metric tons of steel being produced per minute per strand. So, enormously efficient process. A lot of developments went in the last 150 years, and we have been able to reach here, achieve all these marks, because we have relied at all stages heavily on fundamentals. The application of fundamental knowledge is extremely important in steering the technology further, because there is going to be many challenges coming up in the future days for steel making. For example, stricter environmental regulations, and burning of fossil fuels, specific energy consumption. These are recycling. These are some of the fronts where the steel makers will be more and more concerned to improve, and there we will see that the science based foundation will come to our rescue, and we will have to increasingly apply the fundamental knowledges in order to find the ways out. Now, there is a huge knowledge based foundation of steel making. This I call as a knowledge based foundation of steel making. I will tell you what is the components with a top down approach. So, if your knowledge based foundation of steel making is good, what you can do? You can do very well process analysis, design, control, optimize, optimization. And if you can do all these things, then what is the net result? The net result is enormous. You are talking of you can develop new technology, people are looking for direct steel making technology, people are looking for technology where they do not have to use coke to produce iron. You can have new products, every day. You see, new alloy systems are being developed, new products are being marketed, and what was not possible 20-30 years back, these are possible today. I mean, for example, IF grade steel. Who heard about IF grade steel 30-40 years back? Today, you can roll sheets, grade steels, and make thin automobile thin sheets ready for automobile usage, and these have been the development of sustained application of knowledge. You can reduce specific energy consumption, you can improve yield, you can decrease emission, and make the process more environmentally friendly. Today, steel industry is looked down upon in view of the global warming, that we are one of the biggest polluters as far as the greenhouse gases are concerned, and we got to tighten our belt, and there we will find that in the context of direct emission, decreasing emission, reducing specific energy consumption, process analysis design will play a very big role, and this is based on the knowledge based foundation. And what does this knowledge based foundation comprises of? It has 4 different components. These are very important. Steel making, we say that this is the manufacturing steel making, or the alternative that I can put here in the box is the manufacturing. Then we have the science based foundation, I have modeling, and I have measurements. So, manufacturing process, science based foundation, modeling, and measurements, they constitute our knowledge based foundation. You cannot omit any of this. So, you have to know the steel making technology, the processes, steel making processes very well. You have to know the science based foundation of steel making. When you talk of the science based foundation, let us elucidate what does it contain. The science based foundation of steel making contains, for example, metallurgical thermodynamics, that is why before a student or one takes a steel making course, it is so important for him or her to know about metallurgical thermodynamics, which is introduced at the second year level or third year, beginning of the third year level in engineering program. We have to know about metallurgical kinetics, and kinetics basically comprises of 2 components. We will subdivide kinetics into rate phenomena and chemical reaction. Rate phenomena again can be divided into 3 sections. We can say fluid flow, heat transfer, and mass transfer. So, you see the science based foundation of steel making is extremely vast, and on top of that I can say that multiphase or gas liquid interaction. Basically, I am talking of gas metal interaction, because these interactions, as in the case of a basic oxygen furnace, these are reacting interactions. On the other hand, in the case of an argon molten steel interaction in a ladle, these are inert interaction, there is no chemical reaction. So, we have to know thermodynamics well, we have to know metallurgical kinetics well, and there we see that it contains of various subjects, and each of these can be a topic on their own, and in many engineering disciplines like mechanical engineering, chemical engineering, we have full-fledged one semester courses running on this. So you can imagine the breadth of the science, and it is here that you get the largest insight. Unless your science base foundation is good, you will not be able to build models, and if you don't build models, you will not be able to make any meaningful interpretation of the measurements that you might intend to carry out. So therefore, we have to know these subjects well, and most of you during your second year stages of metallurgical engineering program have been exposed to thermometallurgical thermodynamics, also a subject titled differently, maybe transport phenomena or heat transfer, and then many of you may not have really done an exhaustive treatment of metallurgical kinetics and metallurgical kinetics, which comprises of so many things, but in an isolated way you are already exposed to it. So I intend to revise this very briefly, because as I said, they are subjects on their own, and when I am delivering a few lectures on the topic of steel making, perhaps it will be beyond any possibility to address these subjects on their entirety in the context of steel making, but nevertheless it is important for us to review certain key concepts before we can advance into the discussion of various other topics, basic oxygen steel making, ladle metallurgy, continuous casting, etc., because there will see extensive application of the fundamentals. So before we can address all those advanced topics or relevant topics, it is worthwhile for us to briefly examine the key concepts of thermodynamics, metallurgical kinetics that are relevant to steel making. So let us talk very briefly about the key concepts in metallurgical kinetics first, metallurgical thermodynamics. So, it is a vast subject, as I have mentioned, but in the context of steel making, we apply metallurgical thermodynamics particularly to compute or calculate the state of equilibrium of the system. So, in many instances we would like to see whether this process has reached equilibrium or not. For example, we can say carbon oxygen reaction is taking place in a basic oxygen steel making converter. Is the reaction closer to equilibrium? How far it is from the equilibrium? If the reaction, when the reaction reaches equilibrium at a certain temperature and pressure, what is the composition of the system in terms of its carbon concentration and oxygen concentration? So all these equilibrium calculations we wish to calculate, we wish to perform in the context of steel making. For example, I have a slag and I want to find out that how much of iron oxide would be there in the slag in equilibrium with a certain given concentration of oxygen. So I will carry out an equilibrium calculation and I am going to find out that what is the level of iron oxide content based on that equilibrium concentration. It is not necessary that the prediction is going to calculation is going to match the measurements. It is only going to match the calculation is going to match measurements provided the process has truly reached the state of equilibrium. Thermodynamics, for example, as you all know, it predicts about the feasibility of a process. Okay, thermodynamics, it depends on the initial and the final stage. It does not depend on the path. Okay, so to study the feasibility of a process, we apply thermodynamic fundamentals. So whether oxygen will react with carbon or not, the feasibility of that process we can examine. But if the process is occurring, then it is away from the equilibrium, because at equilibrium there is no net rate of the process, it is standstill. Okay, so thermodynamics cannot talk about rate, it can only talk about the feasibility of a process, it can talk about the state of equilibrium of a system. When the process is occurring spontaneously from one direction from left to right, for example, carbon and oxygen reacting to form carbon monoxide, there comes the question of rate, that if it is reacting and the reaction is proceeding in one direction, if it is moving towards equilibrium but not yet at equilibrium, then the question comes at what rate it is happening. You know, I have quoted that 2 to 3 kg of carbon per second, that is the rate of carbon elimination. That means if you are talking of carbon oxygen reaction, okay, the reaction obviously is going in the forward direction, and certainly it is not close to equilibrium, which we represent basically as a reversible sign. No, when you are talking of 2 to 3 kg of carbon per second of removal, that means we are talking about the reaction being going in the forward direction. Now, what is the condition for a process to go from the left or a reactant to be converted into a product. Or in terms of a system generalized statement, we can say that the free energy change is going to be less than 0 for the reaction. In that case, we can say this is going to be going from spontaneously from left to right. So, delta G essentially means that the product has a lesser free energy than the reactant, and therefore, this is a negative quantity, and the free energy becoming negative gives a essential condition for spontaneity of a process. So, this criteria we have applied in many cases. Now, let us look at that when you have a reaction like, for example, and let us say that the reaction is occurring reversibly. That means it is close, operating close to equilibrium, and then we say we have so this is the chemical reaction that we wish to represent. So, we have a forward reaction, we have a backward reaction, they are competing with each other, and soon the process is going to be under equilibrium condition. In this particular case, okay, the expression that we have seen or we know from our knowledge of thermodynamics is delta G, the free energy change for the reaction is the standard free energy change plus the gas constant logarithmic, and then we say it is activity of L raised to the power L, activity of M raised to the power M, activity of A raised to the power A, and activity of B raised to the power B. And we know that if the process is occurring close to equilibrium, in that case, there is the product and the reactant will have free energies which will be identical. So, there will be this quantity on the left hand side will be close to is equal to 0. Now, this quantity, this is called, as we have known, mind it, I am not trying to introduce all these concepts in great detail, because I am expecting that you know the subject, you have been exposed to thermodynamics. We are just revising it very quickly, so that we find these concepts to be later relevant, and we can remember them often as we advance or move on to different topics in steel making. So, this is, as you know, this is activity quotient, and when the process is at equilibrium, if the chemical reaction is at equilibrium, as I have tried to equilibrium, then we say that delta G naught is equal to this. We have applied frequently to solve a variety of problems in thermodynamics, particularly for steel making systems, for solutions, and so on. And this term, these are now, we must denote that these concentrations refer to the concentrations at the equilibrium state. So, one should normally represent this with a suffix like AL, capital L, comma E, A small m, capital M, comma E, and so on, to indicate specifically that this, when you write delta G is equal to 0 at equilibrium, delta G being equal to 0. So, the equation translates to this particular form, and this now refers to the equilibrium concentrations, and as I have written here, these are essentially activities. Okay. Now, this concept, the delta G and delta G naught, have been extensively applied, and what is the delta G naught essentially implies? Delta G naught implies it is the standard free energy change, okay, when the elements or the reactants and the products are assumed to be in their standard state, okay, which we say as a 1 atmosphere pressure, and that is the condition at which delta G naught is going to be evaluated in terms of this. Now, in order to evaluate delta G naught, we must understand that we have to have proper activity versus composition relationship. Okay. So, we must know, because we will not be able to directly measure activity. Okay. It is activity is a measure of chemical potential in the system. So, what we can do, we can measure the concentration. Based on that, we will be able to evaluate this activities. And therefore, there are various models which are available to us, and which will allow us, for example, to convert activity in terms of relevant known parameters. For example, if I say that, well, the system that I am talking about, in the context of particularly solutions, because we talk of steel making, molten steel and slag can be visualized as solutions of multi-component system. And if I say that activity is roughly equal to mole fraction, okay, in that case these activities can be converted into corresponding mole fractions, and mole fractions can be easily converted into wet fractions, which are measurable quantities through any standard chemical devices. Okay, before I talk about this activity composition relationships, whereby we can convert these equations or expressions in a more meaningful form, let us explain the context, the relevance of a parameter called the free energy of formation. So many a times you will find that in the literature, free energy of formation of compounds are extensively used. For example, if I start with a compound, and you will require, in order to carry out that, what is the difference in the free energies, you will have to know that, the compound that you are taking, what is the free energy of formation. For example, I can write down, say, a metal plus oxygen, and then I say it is mx/y. So therefore, it is going to be 2 by y, and this is going to be 2x by y. So this is a stoichiometrically balanced equation, as you can see here. Okay, let us denote it in the equilibrium condition. Now, so this oxide I can use, for example, what is the free energy of formation of this particular oxides? What is the relevance of this? Because I may use these oxides in other calculations also. For example, when I say that, well, I take iron oxide and I want to find out the free energy change for this reaction CO2 plus Fe, then the issue will come that what is the free energy of formation of this compound, then only I will be able to find out the free energy. So I will have to find out the free energy of formation of iron oxide, I will have to find out the free energy of formation of carbon monoxide, I have to find out, because these are all compounds. So only when I know the free energy of formation of these compounds, then only I can calculate the net free energy change for this particular reaction. So we have free energy of formation of the sulfides, we have free energy formation of the chlorides, we have free energy formation of oxides. So these are very standard informations which are needed for carrying out many pyrometallurgical calculations, and I am going to just explain, you already know, I am going to highlight this free energy formation in the context of oxides, which is known as where it is tabulated, is known as an oxide Ellingham diagram, to which all of you have been exposed with. Now here, for example, I have written this x and y are the stoichiometric compound. So you can imagine that if I am talking about aluminum, then what is the value of x? So for aluminum, we know the corresponding oxides is Al2O3. Okay, so it turns out that x is equal to 2 and y is equal to 3. That's what I am talking about. If it is iron oxide, in that case you can also clearly see that what will be the value of x and y for all other oxides you should be able to visualize. Now, free energy of formation, standard free energy of formation, standard state, that means the metal is in the pure state, the oxide is in the pure state, as a function of oxygen partial pressure, has been measured by various investigators, and for the sake of our convenience, so that we can carry out thermodynamic calculations very easily, these have been tabulated before us. And in the Ellingham diagram, if one assumes that, well, delta G naught formation can be represented in terms of A and Bt. Now you can see that this is a Gibbs free energy expression. Gibbs free energy functional is expressed in terms of combined expression of first and second law as enthalpy, temperature and entropy. And if you assume that, so therefore I can say that, well, if you assume that H naught, standard enthalpy and standard entropy of formations are not not dependent on temperature. In that case, the free energy of formations of oxide materials can be expressed conveniently in terms of this particular equation. So, that means it indicates that the free energy of formation plotted against temperature will yield us a straight line in which A and B are constants, and that is what you actually see when you look at the Ellingham diagram, where you have a number of straight lines drawn, and I am going to now draw it very briefly and show you that what are the relative positions of the lines in the figure and what does that really indicate. So, at equilibrium, when delta G is equal to 0, I have shown that delta G naught is equal to this parameter, and this, as you all know, is called the equilibrium coefficient or equilibrium constant. And if I look at now this reaction operating close to equilibrium, I should also be similarly write down the equilibrium coefficient, and that is going to be activity of metal oxide raised to the power 2 by y, and then activity of oxygen, and if you assume ideal behavior, then I am going to say that this is equal to partial pressure of oxygen in the system, and then we have activity of metal raised to the power 2x by y. Since we are talking of standard free energy change, so that is why we will, the standard state is the pure for metal and metal oxide. So, therefore, their activity is going to go to be equal to 1. So, this is equation will going to come out to be partial pressure raised to the power. So, therefore, now one can measure the partial pressure of oxygen, and delta G naught is exactly going to be is equal to RT ln PO2. The negative sign cancels out, and that is what it is, and therefore, we can now study the equilibrium of this reaction at 800 degree centigrade, 900 degree centigrade, 1000 degree centigrade, measure the partial pressure of oxygen, and on the basis of that we can compute the delta G naught value, because R is known, temperature is known, and partial pressure is the equilibrium partial pressure that we have measured through a adequate measuring device. So, we should be able to now at various temperatures we should be able to plot. So, temperature is measured, temperature at which the equilibrium has been obtained, corresponding delta G naught is estimated based on the measured PO2 value, and we should be able to draw now a straight line between the two, because of the fact that delta H naught F and delta S naught F are largely independent of temperature. And if you look at it in such plots, you will find that there are straight lines, and only the slope of the straight line changes when there is a phase change. Okay? For example, we may have started with a solid, but then at some point of time the solid may melt. So, otherwise when the phase is maintained continuously unique, in that case you will see that there is a straight line, and this straight line behavior for different metal is going to be different in the system. They need not be parallel, as I have tried to indicate. In fact, there is a straight line, there is a line which is horizontal in the Ellingham diagram, and there is a line which is actually with a negative slope. These are the two peculiar lines in the oxide Ellingham diagram. So, this I say as delta standard free energy of formation of oxide, which is actually equal to RT ln PO2. So, now these are the negative values. For example, this could be something like 1200. So, kilocalories per mole, and this could be about minus 200. So, more negative value is the standard free energy formation. So, therefore, this line indicates that the values are here, standard free energy change values are far more negative than this value, which essentially indicates that a very little amount of oxygen will be able to oxidize this metal, then it is possible for this particular metal. So, a very low lines in the figure, for example, will be for 2 calcium plus oxygen, and note it so that we can compare the relative affinity of elements or the stability of oxides at a given temperature. All this is done for per mole of oxygen, and this is 2CaO, which essentially indicates that calcium oxide is a very stable oxide. On the other hand, if you look at iron oxide, for example, Fe 2Fe plus O2, it is going to be relatively. So, these are all at equilibrium. So, therefore, I should maintain, and calcium, then will come magnesium, then will come aluminum, then will come titanium, then will come silicon, and if you go up, and then you see lead oxide, tin oxide, etc., which are relatively weak oxides. And this line is the CCO line, and this is the COCO2 line. You must be knowing that why the slope of the lines are different, because of simply the difference in the entropy values for these reactions, and it's a standard entropy that causes a opposite slope for carbon monoxide and carbon dioxide lines. This you must be knowing. So we have similar figures which are tabulated, and these figures give us important guidelines as far as pyrometallurgical processes are concerned. For example, at this particular point, when carbon monoxide line intersects this particular line, for example, it tells us that it should be possible to, below this line, the dotted line carbon monoxide line occupies smaller position. So therefore, lower position. So therefore, above this temperature, carbon monoxide is far more stable than the oxide which is corresponding to this particular line. So therefore, it indicates that beyond this temperature, if you go beyond this temperature, carbon monoxide will be able to reduce this particular line for the oxide itself. And now we see that, well, carbon monoxide line intersects the FeFeO line at 800-900 degrees centigrade, but it intersects the alumina line, for example, at more than 2000 degrees centigrade, and that's why by looking at this diagram we can immediately conclude whether carbothermic reduction of a metal oxide is possible or not. Similarly, we have sulfide diagrams also. Per mole of sulfide, we can find out that what is the standard free energy change, where we can take a metal, take sulfur gas, and then form metal sulfide, and exactly the same sort of graph can be produced, and which is known as the sulfide Ellingham diagram, which gives us important clue regarding the pyrometallurgical or the smelting, sulfide smelting processes. Now coming back to, this is a, for example, you see how smartly I have been able to convert. I made one assumption that, well, activity of oxygen is equal to partial pressure of oxygen, okay, and ideal behavior has been, ideal gas law has been assumed, and thereby I have been able to convert the oxygen activity into partial pressure. So I have assumed an activity composition relationship here, okay, and now we have various models, particularly for steel melts and slag. One model for particularly solutions, when we are talking of activity, we are talking about activity of sulfur in steel melt. So basically we are talking about activity of a species in a solution. So we have for various solutions we have various models available, and as you all know, Raoult's law is there. So if you have concentrated solution, in that case you can say activity is equal to, actually activity of I is equal to mole fraction of I. And then if you have departure from Raoult's law, you introduce what is known as activity of I is equal to, introduce an activity coefficient and into xi. Okay. So Raoult's law you all know. For example, iron and manganese. Iron and manganese, they occupy very close position in the periodic table. Their atomic numbers are similar, crystal structures are similar. So when you mix iron and manganese, they form ideal solution. And there you can say that, look, if the weight percent, if the mole fraction of manganese is 0.5, in that case its activity is also equal to 0.5, because iron and manganese obeys. But there are only few solutions, few systems which are truly ideal in nature. Most of the systems are non-ideal, and departure from the Raoult's law is expressed by what is known as the Henry's law, where we say that activity is equal to activity coefficient, and this can enhance the activity, can get enhanced bigger than the mole fraction or can get smaller than the mole fraction depending on the value of gamma I, the activity coefficient. If activity coefficient is greater than 1, then we say it is a positive deviation. That means if mole fraction is 5, in that case the activity will feel like it is 0.7, 0.8 or something like that, because activity coefficient is greater than 1. So activity coefficient greater than 1 causes positive deviation, and activity coefficient less than 1. So we have, this is the Raoult's line, Raoult's law line. Activity is equal to mole fraction with an angle of 45 degree. What is there? It is activity of I, it is mole fraction. And this is the negative deviation. For example, this is the negative deviation, and this is the positive deviation from the Raoult's law. And that deviation behavior is explained on the basis of this expression. Now, we can have different type of expressions also depending on what we choose as the standard state. In this case, the standard state refers to the pure element, okay, but we can also define a standard state. For example, we can use Henry's law in the weight percentage standard scale. So, 1 weight percentage standard scale. This is also a very popular scale and finds extensive application in dilute solutions, and there we say that activity of a species I is approximately equal to weight percentage I, and therefore activity becomes equal to unity when weight percentage I is so when weight percentage I is equal to 1, then the activity is going to be equal to. So, this is the Henryan activity in 1 weight percentage scale. This is interpreted as the Henryan activity in concentrated or in the pure state when the elements are in their original solid state or in pure state, and this is with reference to 1 weight percentage standard state. So, there are the free energy, standard free energy of formation, if you calculate, for example, with respect to 1 weight percent standard state or with respect to pure element as the standard state, these values are not going to be related. So, there are going to be some difference by some constant amount when the thermodynamic parameters are evaluated with respect to different standard states. So, one standard state, it is like a frame of reference. You have you can do the coordinate transformation from one frame of reference, you can shift the origin and go to another frame of reference. So, exactly the same thing is applicable here. It is based on only our convenience that we use sometimes pure element as the standard state, or sometimes pure compound is the standard state, or sometimes 1 weight percentage as this one. So, this will essentially tell that that this activity is equal to 1. So, this is mole fraction is equal to 1 and this is activity is equal to 1. So, this is 1 and this is 1. So, one activity, so mole fraction is equal to, or you can say it is not mole fraction, but weight percentage. So, this point is actually 1 weight percentage and this is actually activity is equal to 1. So, at the pure state we have reference with pure elements or pure compounds, we can have one standard state defined, and with respect to 1 weight percent standard state we can have again the same kind of an evaluation. Now, if weight percentage is equal to 2, in that case what happens? If Henry's law is obeyed up to that, the activity does not become equal to 2, it becomes equal to 1, because that is the maximum value of activity that is actually possible. Now, this assumes that up to 1 weight percentage Henry's law is obeyed in that 1 percentage standard scale, but if it deviates from that, in that case we can introduce a parameter which is weight percentage of I, and this Fi actually given in terms of the composition of the mult, and this is multi-component dilute solutions which have lot of impurities and lot of elements present. This sort of an analysis is very meaningful in the sense that where we can take into account the activity of influence of other elements on the activity of the species. For example, we can say that there is one EI B into weight percentage B plus EI K weight percentage of K. So, this activity coefficient is given in terms of some EIs which are known as the interaction parameters. Again, these interaction parameters are tabulated in thermodynamic books. This tells us EIB into weight percentage of B. So, therefore, it essentially tells us the influence of B on the activity coefficient of I. Now, you must understand that when I have iron and sulfur, for example, okay, I have an activity, I can measure the activity of sulfur. Now, when I introduce carbon into it, so it becomes a now 3-body problem. So, there is carbon sulfur interaction, carbon iron sulfur iron interaction, and carbon iron interaction. So, as a result of which, in a 2-component system, iron and sulfur, whatever is the activity that I measure in the presence of carbon, the same activity will not be measured. So therefore, we understand that the introduction of a third element will either increase or decrease the activity of the second element, and therefore all the solutes present in steel melt will have, for example, influence on the activity of a given species. For example, if you take the activity of oxygen, okay, so the activity of oxygen will be dependent on the activity of sulfur, on the activity of phosphorus, how much phosphorus is there, how much silicon is there, how much manganese is there. So on all these things, and that is dictated by Fi and the dependence of Fi in terms of the weight percentage of various species. So you can interpret this to be as oxygen, I is oxygen here, and this B may be silicon, K may be aluminum, and so we have a multifaceted influence of all the solute elements over any element, and thereby its activity can be either increased or decreased. Now this essentially tells the influence of B on I. Now we also have parameters called EII, which is called as the self interaction parameter. Okay, and the self interaction parameter sometimes may become 0 and sometimes may not become is equal to 0, but they nevertheless come into the picture when you formulate Fi in this particular form. So this parameter can be known, okay, but for example, if there are self interaction parameters, then and I can know that how much percentage of manganese, for example, is there, and then I can say that these values are known from, these are experimental values available to us, values which are available to us. So these are known, and these compositions B, K, etc. can be known, but as you see here that Fi itself is a function of Wi. So therefore, when you solve this kind of an equation, we get an equation of this particular form, in which A naught is equal to a constant, because the log term is there, log Fi. So therefore, we can convert the equation in terms of this unknown parameter. So x you can interpret as the weight percentage of I, x plus log xi, which is known as a transcendental equation. You cannot solve these equations analytically, so you have to use computational routines, and you can imagine that so many such equations are going to be there in multi-component system. One equation will be there for oxygen, another equation will be there for sulfur, another equation will be there for manganese, and lot of activities that you are going to calculate, and then as a result of which you may carry out many other calculations. For example, you can say I have aluminum, the deoxidation calculation, aluminum plus oxygen is giving you L2O3. Now, if you assume that there is no formation of any slag, just pure alumina forms, there is no silica, there is no calcium oxide, so pure alumina is there, okay, there is no reaction taking place simultaneously. So aluminum reacts with oxygen, dissolved oxygen, and produces. So we can say dissolved oxygen, 2 times dissolved oxygen and 3 atoms of aluminum producing 1 molecule of Al2O3, and if this is formed in the pure phase, there is no formation of any compound, then we can say that the activity is equal to Al2O3 is equal to 1, and then I can write down that the K equilibrium is actually activity. So this is equal to 1, and then I can say this is going to be Henrian activity because it is dilute solution, okay, does not obey. So this is HAl, and then we have HO, and then this is equal to 3 and this is equal to 2. If there is an indication that up to whatever oxygen is there below 1 weight percentage that you all know, okay, as I have indicated, it is about the saturation limit is about 0.20 weight percentage. So we can say that as an approximation we can say that this is equal to weight percentage aluminum cube and weight percentage oxygen square. Now free energy of formation of Al2O3 is available to us. Note that this free energy formation and the free energy of formation in the aluminum diagram are not going to be identical, because here the standard state is different. There the standard state was pure aluminum, but here the standard state is 1 weight percentage. So, the value of free energy of formation for this equation cannot really be directly obtained from the Ellingham oxide Ellingham diagram. This is the point, because we have changed the standard state. So, this sign is very important for us. This is an approximate sign. Otherwise, if there is a departure, we should have introduced the parameter Fi into this particular calculation, and it would have made the calculation a little bit more tedious. If I substitute in this particular form, in that case I should be able to use a simple calculator and solve it, but the moment I introduce Hi values here, HAl and HO, the calculation becomes complex. We have to take into account manganese concentration, sulfur concentration, silicon concentration, and as a result of which we will require computational routines to solve, because we generate equations of this particular form which are not normally, which one cannot really solve by analytical means. So, therefore, we have to have today large computer routines in order to calculate the state of equilibrium, give us the composition, give us the phases, concentration, etc. Many computational packages are available. So, maybe you have heard about this software which is called the FACT, a Canada based software for thermodynamic calculations, facilities for chemical thermodynamics, calculation of chemical thermodynamics. It is chemical thermodynamics. Then we have Thermodoc. This is another software which is available. Thermocalc, which is another software. There are a lot of software platforms which are now available where we can perform many complex thermodynamic calculations considering multi phases, various types of solutions, and innumerable number of possibilities to predict the various states of equilibrium that you may be interested to know. Now, beyond this, one important parameter that we often talk in oxygen steel making is a term called oxygen chemical potential, or oxygen chemical potential of oxygen. This is a very important term which we frequently use, and chemical potential is our notation for chemical potential is mu, and mu is basically written for a species I is equal to mu I naught plus RT ln I. That is the chemical potential of this is a standard formulation, accepted, well accepted formulation. This is the standard chemical potential of the species. This is the activity, and this is the chemical potential under consideration at a given under a given condition. Now, transport of species from one phase to another phase is driven by chemical potential. So, we have thermal potential. Thermal potential is created because of a temperature gradient. Heat will flow when there is a temperature difference. Now, mechanical potential is going to be created by head difference or pressure differences. Similarly, mass transport is going to be created because of gradient in chemical potential, which is directly related with activities. We must understand that when we have studied this famous Darkins couple, we have seen that in terms of concentration, it is possible for us to transfer carbon from a region of lower concentration to a region of higher concentration, because of the simple fact that in the lower concentration region carbon, actually the activity of carbon is much more because of the presence of many other solute elements which have influenced through the activity coefficients, okay, and enhance the activity of carbon. So, it is not the absolute value of concentration that dictates the rate of mass transport, rather the possibilities of mass transport or transfer of a species from one phase to another phase is going to be dictated by the chemical potential. So, therefore, chemical potential is a very, very important term in the context of mass transfer studies, and also oxygen potential is a very important term. It then tells us that what is the level of oxygen potential in the system. It tells us the oxidizing power of the system. For example, oxygen potential in a blast furnace is extremely small, okay, 10 raised to the power minus 19 atmosphere. This tells us that the environment within the blast furnace is extremely reducing. On the other hand, in in oxygen steel making converter, the oxygen potential because of the presence of oxygen is tremendously large. Now, if you say that therefore, if I have a slag here and if I have metal here and a species I is being transferred from here to here and an equilibrium is going to be achieved. So, you visualize it like this, temperature is higher here, temperature is lower here. So, heat will flow in this direction and heat flow will come to a standstill when the temperature will become identical. Now, if the species I has a higher chemical potential in slag, lower chemical potential in slag, the transport is going to take in the direction of slag to metal and a chemical equilibrium. So, that was the thermal equilibrium when we are talking about temperature. Now, a chemical equilibrium is going to be established at the interface. That means, there is going to be no net movement across the interface, okay, provided the activity is identical or chemical potential is identical here. Now, therefore, if you assume that the same one is, say, this is metal, which I denote as this, and this is slag, and if I assume that the same standard state condition applies. So, I am going to denote by the same bracket, although these are first brackets, this is a third bracket, because I am making an assumption that the same standard chemical potential holds good or applies to both slag and the metal phase, and then we can say that RT ln activity of AI in the slag phase. Now, since these two quantities have been assumed to be identical, so equality of chemical potential essentially implies that when there is a chemical equilibrium, we must have activity in the slag phase of I is exactly equal to the activity of I in the metal phase, and that is the essential condition of chemical potential. Now, we can find out chemical potential. For example, chemical potential of oxygen will be defined as mu O2 is equal to mu O2 0 standard plus RT ln PO2. That is the fundamental definition of chemical potential. And this term, because it is in the pure state, so if you assume that there is only oxygen available, then this term is going to be equal to 0, and therefore, the chemical potential is going to be directly related with the partial pressure of oxygen. So, we can calculate the chemical potential for oxygen potential with respect to this oxygen also, okay, and then translate it, convert it to this particular scale, because here the standard state and here the standard states are different. So, this is the fundamental definition of oxygen potential, and we can calculate the activity of oxygen and the oxygen potential here and then translate it to this particular format. So, wherever there is oxygen, it is possible for us to calculate the chemical potential of oxygen and thereby tell that what is the oxidizing power of the system itself. Okay.